אז בוקר טוב וברוכים ליום עיון החמישי בנושא תאוריה של מדעי המחשב כאן באוניברסיטה הפתוחה. שמי תמיר טסה ואני מהמחלקה למתמטיקה ומדעי המחשב כאן. And I will switch to English because we have some guests from overseas. So good morning and welcome to the 5th Israel CS Theory Day at the Open University. This is the 5th time that I stand here and deliver the greetings at the beginning of the Theory Day. In the first 2 years, I did it as the department chair, and after ending my position as the chair, I continued to stand here and deliver the opening greetings as the organizer of the day. And despite my basic dislike for organizing things, I must say that this task is a pleasure because of the continuing success of those days, and also because those days became the main annual meeting of the community of CS theoreticians in Israel, and our invited speakers gladly accept our invitation to come and participate here. So far, we had over 400 attendees in those days, including undergraduate and graduate students, faculty members and practitioners from all over the country, and also some guests from abroad. We also had 26 invited speakers so far, and that number will grow today to 33. As this year is the Alan Turing year, it is interesting to note that more than 6% of that number, 33 invited speakers, are Turing Award laureates, namely 2 Turing Award laureates. Last year we had Adi Shamir, and this year we have a special privilege to have here the first Israeli Turing laureate, Professor Michael Rabin. We have today 3 sessions with 7 talks of 45 minutes each. The speakers today are Krauthgamer from Weizmann Institute, Michael Rabin from Hebrew University and Harvard, and Ryan Williams from Stanford. They will speak in the morning session. After lunch, we shall have the second session in which Yuval Ishai from the Technion will speak, and then Niv Buchbinder from the Open University. Finally, Ronen Shaltiel from Haifa University and Yossi Azar from Tel Aviv University will speak. The 3 sessions will be chaired by friends of mine from the department here. Mike Langberg will chair the first session, then Zeev Nutov, and finally Tal Hasner. At this point, I would like to invite the Vice President of Academic Affairs of the Open University, Professor Judith Gelezer, to say a few words. Judith.
Good morning, everyone. I just want to tell you that I didn't see the leaflet and the website before, and I didn't plan my address this morning with it, but I'm glad it came out like this, the colors. Okay, we are honored to host here at the Open University of Israel the 5th Israeli Computer Science Theory Day. In the academic environment in Israel, the Open University is different from the other universities in its admission policy and study methods, being a distance education institution. But it is similar to the other institution in its pursuit of excellence, research and development, course development, and teaching. This day is a proof, if we may borrow this word, of its commitment to superior scientific and scholastic standards. This year, as mentioned, the Turing Centenary year, we are honored to have here with us the Turing recipient, Professor Michael Rabin, and who knows, maybe future Turing recipients. Professor Rabin will also be one of the 3 keynote speakers in the ETC conference, which will be held in Haifa at the beginning of July. The ETC, Innovation and Technology in Computer Science Education, is a scientific conference in the sense that research papers are submitted, rejected, or accepted. However, we try to give it a Turing touch, inviting 3 keynote speakers. Michael Rabin is one of them, and the 2 others are Linor Bloom and David Harel, who will talk on Turing-related issues. I may have mentioned it last year that in addition to the excellent computer science research community we have here in Israel, we also have a worldwide known CS education research community, and this is why we can host this year the ETC conference. Our high school computer science program is considered worldwide a breakthrough. For the last, say, 15 years, it was an elective like physics, chemistry, and biology. However, unfortunately, a decision was taken a few months ago to eliminate computer science from the fall. This decision is now on hold, and I still hope to convince whoever should be convinced that in the 21st century, computer science should be placed on the same par as physics, chemistry, and biology. As the Science 2020 report says, we believe that computer science is poised to become as fundamental to science, and in particular the natural sciences, as mathematics has become to science, and in particular the physical sciences. Or, as in the special paragraph for CS education, take far bolder measurements to interest children in science, urgently and dramatically improve the teaching of mathematics and science in schools, and make teaching of computing more than just IT classes, make principles of computer science such as abstraction and quantification a core part of the science curriculum. I would like to thank Tamir for putting together this day. Thank you, distinguished presenters, and thank you all for coming. Let me close with a quote from A Mathematician's Apology by Hardy. If intellectual curiosity, professional pride, and ambition are dominant incentives to research, then assuredly no one has a fairer chance of gratifying them than a mathematician. And one should add, or a theoretical computer scientist. Let's have a great and fruitful day.
Thank you, Judith. I would like to thank Chagit Messer-Yaron and Judith Galezer, the president and vice president of the Open University, for supporting and also encouraging such events here at the Open University, not only in computer science, but in all disciplines. Also, my thanks go to my friends from the department for their help, and especially to Tzipi Ehrlich, the chair of the department, Ninette Khalfon, the department administrator, and my friends Mike Langberg and Danny Reichman, who helped me a lot. In addition, many thanks to Daphna Greenbaum, who orchestrated the operation of this day. So it is time to start. Please remember to turn off your whatever makes beeps, and let's all have an enjoyable day. And Mike, please, the podium is yours.
Thanks for coming, and we're going to start. So I'm extremely happy to invite the first speaker of the session. This is Krauthgamer from Weizmann Institute. Roby finished his PhD in 2001, joined Weizmann after he was abroad at Berkeley and had a position in IBM Almaden. And his research is on algorithms and combinatorics. And he's going to speak about, I hope at least, let's see. I think it's efficient algorithms via precision sampling. Is that true?
Yeah.
Good.
Okay. So, thank you. Okay, so thanks for inviting me. Let's see if I can manage this one. Okay, and thanks for coming. This is a joint work with Alexander Andoni and Krzysztof Onak. So let's think about the following goal. We want to compute the fraction of Dacians, right? These are people from the country of Dacia, from a long time ago in the ancient empire. And let's suppose that's our goal, right? Some problem of estimating the fraction of these people in the entire empire. Okay, it's basically like an estimation or sampling problem. In general, I mean, this is going to be the example, the running example. In general, think of like estimating a summation, a sum S, which is A1 plus A2 plus until AN, where each element AI is in the range 0 to 1. Okay, so it's not exactly the same problem in the picture, because let's say that in every country, we want the sum of fractions of people, or let's say in every country in the empire, we have exactly 1,000 or 1 million people. So what the natural approach would be to sample or subsample, right? So if you are in the capital of the empire, you'd send accountants or people to some random subset of the provinces, say a set J, and depending on your budget, you choose the size of J. Let's say it's the letter M. Okay, then you count the number of dayscents in each place, you add up, and you get an estimate. Right, so the estimate is going to be the summation. Okay, so this is supposed to be summation in J, right, in your subset, what the number that you count, and then you scale it by n over m, which is the ratio that you subsampled, right? So that should be the ratio that you sample. Now, if you do the calculation, it's not difficult to see that what you expect to get using something like, say, Chebyshev's bound, right, like variance estimate, you'll get the following estimate on how close is S tilde to your target, to the real answer S. Okay, so let's look at this for a minute. So there's the factor 2 here and 0.5, so that's like it being off by a factor of 2. So this is, I mean, usually you'd see this like something like 1 plus minus epsilon or some other variations. This is like multiplicative error that comes from standard sampling. Okay, now there's another error term here, which is additive. This is n over m. Right? If you see only, let's say, root n of the variables a1 up to an, you see only root n of them, it seems it'd be reasonable that you completely miss any subset of, I mean, with constant probability, a subset of size root n. Right? Because you read only m elements, a subset of size n over m, there's a constant probability you'll miss completely. Maybe all of these are ones, and everything else is 0. So that's why you get, and you'll miss all of them, and then you have the, or the other way around, so you have an additive error of n over m. Okay? So there are two types of errors here, multiplicative and additive. Okay, I'm going to need both of them. Okay, now the multiplicative, actually, I'm going to kind of neglect throughout the talk. So think of it as being there, but I'm not going to say it. So it's like 1 plus epsilon, or in this example, 2, or something like this, a fixed constant. And we're going to focus on the additive error. So if we want constant additive error, if we want this additive error to be very small, constant, by this estimate basically means that we need n to be of the order of n. Okay, in this technique. And we want to do better. How can we do better? Okay, so this is the framework of what we called in a previous paper, precision sampling. So what you're going to do in this precision sampling, you send your accountants to all the provinces, but you don't tell them to count the number that you need to count, this AI, or the number of the fraction of dayscents. You only require an approximate count. You make their work easier, but then you send them to every province. Okay? So what is the precision that each one of them needs to the precision that each one of them needs to use? Well, it's going to be some number ui, so it's a different precision for every AI, for every province, and we're going to see in a minute how to choose these precisions. But in general, we're going to get an estimate, which is I'm going to call AI tilde, which is an estimate for AI, for the real number. And it's an estimate within additive UI, as you can see in this slide. Okay, really, there's also a multiplicative error. Let's think of it like 1 plus epsilon or something. It's not written here to simplify the notation. But in fact, there is one. Okay, so the challenge is we want to have a good accuracy overall. So the question is how to choose the UIs. Now, of course, you choose them very small. Maybe you choose them like 0 or something. So it's exact, full precision. Then it's going to be expensive. So what we're looking for is a trade-off between our cost, which is described by this choice of UIs. The smaller the UIs, it's like more expensive to compute very fine precision estimates. And the trade-off between these UIs, or this cost, and the quality of approximation that we can get from S. Right? The approximation we get for S is going to be using some algorithm. It's going to use this AI tilde to compute an estimate like S tilde that we had before, an estimate for S. Okay, so I didn't say how, but we want to get a very good estimate. So the question is how to get a very good estimate using relatively low cost. Okay, so now let's do it more formally. This was like the expository part. So we have the algorithm which tries to estimate the summation S. Right? So that's on the left, the estimator. And then we have some adversary which will choose the maybe most difficult A1 up to sequence A1 up to AN. Okay? So think of it as at the same time, the first step, the same time, the estimator chooses the precisions that they want, that he wants, precisions UI, possibly different precision for every AI. And at the same time, there's some A1 up to AN, which is the hidden numbers that are fixed by the adversary. So the adversary does not see at this point what precisions the algorithm is doing, is choosing. And the algorithm doesn't know, of course, the unknown variables A1 up to AN. Now, the estimator asks the input, or somehow, by using this accountants, give me an estimate for this A1 up to AN, and he gets the estimates A1 tilde up to AN tilde, and each one is off by at most UI, okay, the chosen UI. So here, of course, the UIs are revealed to the adversary or to the input. So you can think of this, at this point, the adversary chooses these errors, right? This difference, you can think of it as noise, but it's not random noise, it's adversarial. Okay, so the difference between AI and tilde AI is adversarial, chosen by the same adversary at this point, at the second stage. Okay? So maybe it makes sense in some scenarios to make all the differences AI minus tilde AI, to make all of them positive and as large as possible. And in another scenario, it would make sense to make them random, or, half of them positive, half of them negative. Who knows? Okay, so now the algorithm receives these estimates A1 tilde up to AN tilde, and using these estimates, he has to report some S tilde, some estimate for the summation. And the goal, so I'm making everything overly simplified or as simple as possible. Let's say we want the accuracy of the estimate to be additive 1. Okay, so there's a general version, we'll see it in a minute. But let's think of this scenario. Okay, so we want a very good accuracy. So, okay, if we want such a good accuracy, how much are we paying for it? So this is our cost model. We're going to think of like the average cost. So we have 1 over n. In this font, I know it's a bit confusing. This is not L, this is 1. Okay, so this is 1 over n times the summation of is 1 over UI. So if the precision UI is very small, you pay, of course, 1 over UI, you pay a lot. Okay? And this is basically like average cost. So this models the situation where if you want 1 over UI, this is like the runtime or the query complexity or the sample complexity or the space complexity of your operations. To get accuracy UI, you have to pay 1 over UI in some resource. Okay, and this matches scenarios where this is really some sort of like sampling. And then, like we said before, if you use m samples for the additive error, we had n over m additive error. So it's inverse in m, right? The accuracy and the complexity are inverses of each other. Okay, so here is one example just to illustrate this. Let's suppose we choose all the UIs to be 1 over n. So this is like a very small accuracy. By the formula, every 1 over UI is n, so the average is n. So this is like our average cost. And you can see that if each one has additive error 1 over n, the total additive error is 1. Because for every element I, or AI, we have additive error 1 over n, it would add up to at most 1 additive error. And it turns out that if you do the calculation that this would be best possible if our estimator in this case would just be to take all the AIs and sum this up. Okay, so what can we really do in this model? I'm going to show you. So remember, we're trying to estimate the summation of AIs using these tilde AIs, these additive error estimates. So here is what we call the precision sampling lemma. With a high probability, constant high probability, we can get something like an order 1 additive error and 1.5, let's say, multiplicative error. I told you along the way there's a multiplicative error as well. But if we're looking at the case where the sum S is very small, then the additive error is the dominant one. Of course, if it's large, then the multiplicative error is the dominant one. So we can get something like multiplicative, here it's 1.5, or it could be 2, and constant additive error using average cost, which is only logarithmic. Okay, well, if you remember from the previous example, if I chose each ui to be 1 over n, I get a similar guarantee, but the average cost was n. So this is much, much better. It's logarithmic. Of course, the other one was deterministic. This is going to be, this is randomized. It's only with high probability. So to see what's going on here, here's like a very simple example. Let's suppose we want to distinguish the cases where the summation of these AIs is 3 versus the case where the summation is 1. So it's basically like an additive plus minus 1 approximation would distinguish the two cases. Right? So what are the hard cases for this scenario? So here are two extreme hard cases, or extreme cases for this. One extreme case is the summation is, of AI is, say, 3 because it's 3 ones and everything else is 0. Okay, so maybe there's only ones, like the 3 ones or not a different number of ones, and they're hidden somewhere. What would you do? How would you choose your precision's UI? So then I claim that what we're going to do, we're going to estimate all the AIs, but it's enough to have a very, very crude approximation for each one. We're going to choose UI to be 0.1. Then you can distinguish which AIs are 0 and which are 1. We have a 0.1 estimate, additive estimate for each one. Right? And then we're going to figure out how many 1s are there. And we're going to see, there are 3. What's the average cost here? So it's basically 10 for every I. So the average is 10. It's constant. But here is a different extreme scenario. All the AIs are something like constant over n, maybe 3 over n, or 1 over n, or 2 over n, something in this range. What are we going to do then? Then it makes sense to just sample a few of them. They're all of the same order. They're all bounded. It's important they're all bounded by, say, 5 over n or something. Then we can do a standard sampling argument. And we're going to see that with good approximation, if you choose, we take all the UIs to be only a few of them, basically, and have a very good approximation, which is just like reading them exactly. This 1 over n is just like reading them exactly, because all these errors cannot accumulate too much. So a few of them we're going to read exactly. We're going to see whether the average is more like 3 or more like 1. And we're going to distinguish. So it's a very, very different scenario. We're going to have a few very small UIs, which means that the cost 1 over UI is n, but only a constant of them will pay n. Everybody else is going to pay something like 0 or negligible. So again, the average cost is going to be constant. Okay, so now we need to somehow interpolate between these two extreme cases. Okay, we're going to choose these UIs at random so that we're going to cover all bases, basically. Okay, and that's what's going to happen in this theorem. You can think of it as if you choose, intuitively, you can choose each UI to be something like, say, 2 to the minus k with probability 2 to the minus k or something. So you kind of cover all possible values of UI. Okay, and then you're going to get this scenario. I mean, the interpolated scenario. So if you do this in general, that's the statement that we can prove, is that you can get epsilon additive error and 1 plus epsilon multiplicative error. So this is the formula here. Right? You have additive on each side, there's the multiplicative. And the cost is still log n, but now there's the dependence on epsilon, which is epsilon to the negative 3. And really these two epsilons do not have to be the same epsilon. I'm just simplifying for the slides. Okay, it could be 2 different values. Okay, so you can get arbitrarily good precision or accuracy, where the accuracy here is measured both additively and multiplicatively. Okay, so to illustrate the ideas behind this statement, this theorem, I'm going to use, of course, the simple version with constants, specific constant, not the dependence on epsilon. I want to get the dependence on n to be correct, the order log n. Okay, so here is the algorithm. You choose each UI just uniformly, IID. Okay, and then what is the estimator? Now this is a tricky issue because the UIs are random, but then the adversary sees the UIs and can bias this A tilde to be either above or below the actual values after seeing these values. So you cannot, for example, it doesn't make sense to take just the summation of this AI tilde because they can all be biased in the same direction. Okay? So here is the count that we're going to use. Basically, we're going to take S tilde, our estimate, to be the count of the number of i's such that this, you see this formula, AI tilde, this estimate, divided by UI is greater than 6. And then we have to normalize. Okay? It's some sort of like an indicator. It's an indicator, right? You get 1 whenever this event happens. And you count. Why does it make sense? So this is the main idea here in this line. Of course, you have to do the exact analysis. So what is the expectation of this S tilde, this estimator? Well, by linearity of expectation, if you do a simple calculation, it's the summation over all i's. The probability that this event happens, this AI tilde divided by UI, is greater than 6. Okay? Now, let's try to do the following thing. Here we can multiply by UI. So it basically means that AI tilde is greater than or equal 6 UI. Now AI tilde and AI are off by plus minus 1 UI. So it's the same up to, if you look at the extreme cases, like saying that AI is greater than or equal 6 plus minus 1 UI. Depending on which direction you want to take it, the plus minus 1. It can always work against you because it's an adversarial choice. This plus minus UI, this is the difference between AI and AI tilde, it's adversarial. Okay, so we always have to be careful here, but I'm kind of like summarizing it in a crude description. But if you look at this, okay, we have this 6, so it could be 7 or 5, but now the event is basically like UI is smaller than something like 6, AI over 6. But UI is random, uniformly random. Right, so what is the probability that UI is smaller than AI over 6? It's about AI over 6. Now, depending on the adversary, it could be AI over 7 or AI over 5. That's why we get also a multiplicative error. Okay, so it adds up to our multiplicative error. It's adversarial. But you can see it's like it goes into some constant factor error, no matter what the adversary does. Okay, so it's roughly the summation of AI over 6, and the summation of AI, so up to this factor of 6, this gives us the estimate that we want, at least in expectation.
Where does the 6 come from?
It's this 6. So I wanted to make sure that this 6 plus minus 1 stays like bounded away from 0.
But why 6 in the first place?
Well, it's something that depends on epsilon, but I'm doing here the version without epsilons.
It makes sense if you look about standard deviations and stuff like that.
Yeah, we didn't get, this is just the expectation, right? There's also the standard deviation that you have to do to say that with constant probability, it's good. Yeah, it's arbitrary here. Okay, now this proof would also work if the AIs have, this tilde AI, have multiplicative error. Now not 1.5, I wrote here 1.5, but it should be smaller because then you can absorb it in the, so the multiplicative error that you have in this AI tilde would affect the multiplicative error that you get at the end. So if this is 1.5, you get another 1.5, so it's 2.25 or something. Okay, so that's the main idea. Now, if you do this, what is the cost? This just explains how we deal with this adversarial error, right? In this, using this expectation, and as pointed out here, we also need to look at the variance. Okay, and we do in the paper. I'm just not showing it here, but it's relatively simple. Okay, so what is the average cost? Well, you look at the expectation of 1 over UI, and I claim it's order log n. Now, this is a bit fishy. If you know your math, then it's not true. It's actually infinity. Okay, that's why I wrote after truncation. So basically, you say, well, if the UI is smaller than 1 over n squared or something, then it's just too small anyway. Then I'm going to basically not use 0. The values too small for UI values that are too close to 0, which means values where the cost is too high. There's no point. So if I truncate it, which is going to happen anyway, going to be true anyway, so that's what it means is with high probability. It's conditional expectation or something like this, or truncated distribution. There are two ways to look at it. So since I don't care about values that are bigger than n or n squared, for the summation of AI, right? The summation of AI cannot be bigger than n. So basically, you do this truncation, then effectively for you or for us, it's order log n. Okay, and that's basically proves what I claimed here, that with cost only order log n, I can get a good estimate. Okay, that's in one slide a description of this precision sampling lemma. Yeah, and then in general we get, as I said, this epsilon error, and the cost goes something like epsilon to the minus 3. Now, why do you want to do this precision sampling? Well, I can argue that it's a very natural way to look at the AIs, but here are concrete applications. So the first time we used it was in the problem of computing eddy distance between two strings, and there we use it to save time, to get a faster algorithm. We get something like a polylog approximation to the eddy distance in time which is close to linear. Okay, and the standard algorithm that computes eddy distance exactly takes time roughly n squared. Okay, so this is close to linear but gets approximate answer. And that's the best algorithm known to date. The algorithm actually worked in some sort of like property testing like or sampling, and we use this precision sampling recursively. You can take the big string, you chop it into pieces, you want an estimate for each one. How do you combine these estimates? You have to sum up some values. That's where the precision sampling comes up. Then how you do it in each block or in each piece of the string, you do it recursively. So this kind of, these UIs, or the cost, allowed us to somehow determine how much effort we invest in each block of the string. And it was in a random fashion, recursively. Okay, and the second application, or second reason, is to save space. Space means storage, right? So this is for the problem of computing what's called norms or moments of frequencies in a data stream. And that's what I'm going to tell you about in the next few slides. And this basically, it's a well-known problem. I'm sure many of you have heard about it. So I'm going to introduce the problem quickly. But at the high level, what we get using this precision sampling is a simple and unified approach to compute these LP norms of a stream. Okay? So I hope you remember the precision sampling lemma, or at least roughly what it says. I'm going to change the topic to these norms and then explain how they can be used to solve these streaming problems, these LP norms or frequency moments. Okay, so what is a streaming or a sketching model? Okay, so think about like we have a router. We are going to write the algorithm that sits inside the router. So it's a tiny piece, a tiny small piece of electronics, and it sees a lot of addresses flying, through very quickly. And we want to maintain some statistics of these numbers. Okay, maybe for every IP address, we want to maintain the frequency. How many times have we seen it so far? And the problem, of course, is that we want to log these things for statistics. We don't need exact counts, but we have very small space because the router is very small. Small energy, small memory, and so on. So we're focusing on small memory. So basically, we have this sequence of numbers, which we're going to call them x1 up to xn. Okay, forget it's the IP addresses, but forget about the IP addresses now. You have x1 up to xn, and you want to estimate what's called the frequencies, right? How many times each IP address we saw it so far. And one particular quantity that we want to often want to estimate is what's called the pith moment. It's also called pith norm. It's the same thing, frequency moment or norm. It's for historical reasons, there are different names and different letters. So I'm going to call it the pith moment. It's just the summation over I of xi to the p. It's really the pith moment to the pith power, but That's the way people usually look at it. So if p equals 1, that's very easy, right? Just need to sum up, just count how many packets you've seen so far. Okay. For general p, this problem was studied a lot, starting with this AMS, Alon Matthias Segedi paper that dealt with, for p in the range between 0 and 2, you can estimate it within 1 plus epsilon, the pith moment with space, which is epsilon to negative 2 times log n. This is, okay. So there's a long range of results. So they proved it for p equal 2. It was extended for other p's and so on. It's also important how fast is the update time. Right? Every time you see a new packet, how much work do you have to do? So there are a lot of parameters here. I'm not describing all of them. Usually in this kind of line of work, there are a lot of epsilons and deltas, and I try to avoid all of these things, but there are. Okay, and for p greater than 2, the problem becomes completely different. The space has to be something like dependence on n jumps from being logarithmic to being polynomial. As you can see in the formula, it's something like n to the 1 minus 2 over p. Okay, there's also dependence on epsilon that I didn't write. The first result was by, again, the AMS paper, where they got a polynomial in n, but a different polynomial, and then there were improvements, as you can see here. Here is the general problem. Okay, in general, we have some vector x with n coordinates. Each coordinate is a real value. Usually, we don't think of it as a real value. We think of it as an integer in the range, something like minus polynomial in n to plus polynomial in n. Okay, because we don't want to deal with the accuracy issue, the issue of accuracy. Now, what are the updates? So in general, you can see whenever you see a packet of, it updates some coordinate I, so you increase the coordinate I by plus 1. A more interesting model is where you can see you can also update coordinate I with minus 1. If you update coordinates, so there are like deletions from the stream. If you have deletions, then in an extreme case, this xi might become negative. So that becomes the whole scenario more complicated. For example, the case p equals 1, when I say just count, does it work that way? Now you cannot count because you have deletions. Okay, so it's not like just counting everything. Well, okay, but cheating here, it should be summation of the absolute value of xi in p equal 1. Okay, and then the counting doesn't work. Okay, so this is going to look at this. Turns out that this model is richer, but somehow you can get the same bounds, but things become more complicated or more difficult. But you can get the same bounds effectively. So we're going to look at this more general model with positive and negative updates. And then what do you do? So after you've seen so many updates, the router or whatever small memory algorithm that you're using has maintained some sketch. It's called a sketch. It's a summary of whatever is seen so far. And hopefully it has much smaller than like n integers. We want, so like just like in these bounds, either logarithmically many in n or a polynomial in n, but smaller than n words or bits or something. And effectively this sketch turns out to be very often some sort of an embedding. You map this Rn, from this vector x in Rn, to some other space of smaller dimension. Now, often this mapping from Rn to a smaller dimension, like here, it's a mapping into Rn. So I'm going to call this mapping L because it's linear. Okay, so it's smaller dimension, so it's kind of like compresses your input. But it's also linear, and linear is very useful. Why is linear useful? Because of this formula here at the lower right corner. You have, how do you update when you see a plus or minus EI, an increment or decrement to coordinate I? Well, you already have L of x, what you've computed before. You just need to add up or decrement this L times EI. So you just compute this L times EI, and you add or decrement to whatever sketch you already have. So this is how you update your algorithm. So basically, once you have this linear map, if you use this linear map strategy, you don't need to think about updates. Updates are easy because of this formula. Okay, so being linear is very useful. So we're going to focus on this linear scenario. So here is again a simplified or simple version of the theorem we have in the paper, which is we can compute a linear sketch for LP, for pith moment, with order 1 approximation, using space which is n to the 1 minus 2 over p times log n. So it's basically like the optimal space that is known. There's also dependence on epsilon, which I didn't write, but here it's the constant factor approximation. And in fact, as you'll see in the way the algorithm works, this also gives a sort of like weak embedding, like a mapping between LP and L infinity. Okay, but that reduces the dimension. So here is a sketch of the argument, how we're going to do it. This is basically the algorithm. It's relatively, I told you it's simple and unified, so I'm going to do it for large P, but it's, at least you can see that it's simple. So you choose a random UI in the range 0 to 1. You also choose a random Ri, which is basically just like a sine function, plus or minus 1. Okay, and then you define the following Yi. So remember, you have this Xi. I want to compute a linear map of Xi. Okay, for no updates, nothing, just a linear map. Then everything would work well. So from these Xi's, we compute these Yi's, which is basically multiplying by the sign, and then scaling by this term. UI, this UI that we chose, it's going to be the UI from before, if you remember, but we'll see it in the next slide, to the power 1 over p. Okay, so that's the description of the algorithm. So we have these Yi's. Now what we're going to do with these Yi's, we're just going to hash them. What does it mean to hash them? So every I will going to be a hash function, and every I is going to go into one of the hash table buckets. Okay, and we have to choose the number of buckets appropriately. Here we're going to choose the number of buckets in the hash table to be m, something like n to the 1 minus 2 over p. Okay, so here are the xi's. From these xi's, we compute the yi's by this linear transformation, right? Multiplying. And then we map them into the buckets. Now what happens if two elements, say y1 and y3, like 1 and 3, fall into the same bucket? We add them up. Okay, so this bucket is going to be one counter that contains the summation of y1 and y3. And y1 is just like a scaled version of x1, y3 is a scaled version of x3. Okay, so we're going to add them up and so forth, and we have m buckets. And what's going to be the estimate that we're going to use? So this is how do you store, how do you compress n coordinates into m coordinates. Okay, we also have this randomness. I didn't say it before, but both in the precision sampling lemma and here in these choices, we can actually choose pairwise independent choices. And that makes everything simpler because the amount of memory that we need to store these pairwise independent values is small enough. I'm not going to get into it. But this means that these signs Ri and Rj, say, are independent. Or these are pairwise independent, something about the UIs, and so on. So this also has to be stored, but that's not too difficult. So what is the estimator? So it could be just, turns out that it works for a constant approximation. You can just take the maximum over all the entries in the bucket. You just take the entry in that bucket and you raise it to the power p. That's a good estimate. Okay? Now, what I'm going to show you in the next slide to connect it to the previous discussion about precision sampling lemma, I'm going to use a different formula. But turns out both work. So what I'm going to do in the next slide is actually show you how we got to this, which is using the precision sampling lemma. Okay, but that also works, and that's why it's like sort of like L infinity. It's the max over this h. Now you can see, it's easy to see that this h, this is your memory. It's linear in the input x. And as I said, turns out that the pairwise independence or something like this suffices. Okay, so now let's look a little bit under the hood. Why does this whole thing from before, this linear map, why does it work? Okay, so here is trying to explain it on a single slide. So the idea is that we're going to use the precision sampling lemma to compute this pith moment. Okay, so we have this vector, x, and we want to estimate its pith norm. Now, first step is to assume that the 2 norm is 1. Why can we do it? Well, our map is linear, so scaling is not a problem. We can just take whatever. If we already have this table H, we want to scale it by a factor of 10, we multiply or divide by a factor of 10. How do we? So we only need to know the two-norm. Now we can know the two-norm. That's a relatively simple task known from AMS. Okay, from the paper I said before. It's really relatively a simple task. So we know the two-norm, not exactly, but up to 1 plus epsilon. So we divide by this norm. So we can assume that the two-norm of x is 1. Okay. Now we're going to use the PSL, this lemma, with additive error epsilon, which is small enough. How small enough should it be? Well, it should be small enough compared to this quantity. To this quantity. The pth norm. Okay, like, let's say we want a constant factor, so the error should be at most this quantity. Now this quantity, I don't know how much it is, but it's definitely, I have this bound. So if I make sure that my error is smaller than this bound, I'll tell you in a second what is this. But I know that my error is small compared to this, then it's going to be small compared to this. So we're going to choose epsilon to be, let's say, equal to this. The error from the sampling, for the precision sampling. Why do we have why do we have this inequality? This is basically Helder's inequality. Okay, so it connects the two norm to the pth norm. So it depends on the number of coordinates here, which is n, the dimension. Okay, so basically think of like our epsilon being equal to the term on the left there. Okay, and remember it's actually the two norm is 1, right? We assume that. So basically our epsilon is like 1 over n to the p over 2 minus 1, whatever that. I just want to show you where the n to the factor of n that we get, where does it come from? That's the reason I have all these quantities on the slide. Right? This is the quantity that we get, and this is basically 1 from the scaling. Okay, so now we're going to use this precision sampling. So we have to pick the UIs. You pick the UIs according to the precision sampling lemma, and then we let the YIs to be xi over ui to the 1 over p. That's what we had in the algorithm before. Now, turns out that what we're doing is really the following. We're getting an estimate for each yi to the p. What is yi to the p? Just look for this formula, just xi to the p divided by ui. Okay, so instead of estimating each xi, or each xi to the p, we're estimating each xi to the p over ui. Now, let's suppose we approximate within additive approximation 1. Okay, this is the way we do it with the hash table is really a method of doing what's called heavy hitters, which are if you have a vector and you're trying to find the heaviest coordinates in the vector. This is the heavy hitters. But we're doing it on the vector y, not on the vector x. So it's like the pth power and scaled by this random ui. Okay, and then we do this precision sampling lemma on the coordinates that are written there, yi to the p times ui, which is basically the xi to the p. Okay, so we're trying to estimate, remember these are the AIs that we're trying to estimate their summation, right, for before, which are given by this. So we need a good estimate up to plus minus ui for this. So estimate up to plus minus ui to this is basically like saying that we estimate plus minus 1 for this. Okay, so it's exactly everything fits. If we have a constant additive approximation to these terms, we can actually apply the precision sampling now and get a summation of these terms, approximately. Okay, so if this works and I'm kind of like hand waving or a crude outline, then we'll get a good estimate for the pth norm. But what is the storage that we need for this? Right, the space bound, the storage bound. Well, if you're going to do heavy hitters, well, this hashing trick with this random signs. This is the heavy hitters. So if two things collide, if everything that collides with element I, they have random signs, so they're kind of likely to cancel. Okay, that's the intuition. Of course, it requires analysis, but I'm skipping that part. Turns out that the space bound is controlled by what is the norm of this vector y. Right? You're trying to compute heavy hitters. So this is the most technical slide here, right? So hope you follow or bear with me for this slide. So we're trying to estimate the heaviest elements in y, and up to plus minus 1 additive error. So the resources, the size of the hash table, the storage that we need, depends on the two norm of y, squared two norm. 2 norm squared of y. Okay, the bigger it is, and we want very good, we want to find all of the heavy elements up to plus minus 1. So let's say all of those have value at least 1. Well, it depends how many can there be. And this kind of gives you an estimate how many can there be. Okay, that's going to be your storage bound if you know the literature. Okay, and how large is it? So here is the calculation. Right? We want to estimate this thing, which is a random value. So look at the expectation. We can then apply Markov's inequality or something, but let's look at the expectation. Well, on the term here, the 2 norm of y squared, just summation of yi squared. And each one, now that's linear, so each one is just xi squared multiplied by this 1 over this ui. And the ui is just a random value as we chose. So it's 1 over u to the power 2 over p. Now if you look at that distribution that we had and see what is the expectation of 1 over u to the 2 over p, that's a simple calculation. If you do the version with the epsilons, it turns out to be 1 over epsilon to the 2 over p. Again, remember, I'm looking only at the additive error. There's also the multiplicative error, but that's separate. So it's not going to be exactly matching the paper. But so anyway, what we're going to get is just 1 over. So this is 1 by our normalization. And this is just a simple calculation from the distribution that we have, which is uniform. Right? So we get this there. Now, how do we choose epsilon? We chose it to be equal to this. Okay, that's our choice. Or to get very good, to make the decision something memorable. So you plug in these values and you get this formula we had before. N to the 1 minus Q. The 2 over P, sorry. Okay, so that's where this magic quantity comes from. Okay, I neglected all the epsilons and all the other stuff. There are a lot of them. So this is like the high level where this polynomial in N comes from. And that's the right polynomial, right? I told you the first paper by AMS got a different polynomial, and that turns out there's a matching lower bound and so on. I didn't get to all the history. And that description, this description of the algorithm is generic. Everything works in the same unified way for all P's. So using this technology and variations of this is the basic idea, we got other streaming algorithms. So I told you we got an algorithm for all P moments. We can get also algorithms what's called for mixed norms. So you have a vector of something like n squared coordinates. Think of it as a table, n by n. You compute the p norm on every row, the q norm of every row, and then you combine this using the p norm. Okay, it turns out to be useful for something. Another problem that was studied and our algorithm works, or with small modifications, is what's called LP sampling. You want to sample an element I with probability proportional to this xi to the p, to the pth power. Okay, a sampling algorithm. So it's called LP sampling, and after our techniques were used to get tight bounds later. Now this technique of precision sampling is inspired by a streaming algorithm for Indick and Woodruff that gave this n to the 1 minus 2 over p, but it works kind of different. Over there you have to bucket things or separate things depending on their contribution, on their weight, and this somehow avoids all these things by using this precision sampling, these UIs, which does all the magic for you in combining different values. And it also turns out to be relative but different, distant relative but different from what's something called priority sampling. Okay, so to wrap up, I think I've told you about two applications of precision sampling: one to save time, one to save space storage. It seems like a nice sampling approach, so it should be a natural one, so it should be useful in other cases. I don't know if it's not known to be tight. So what we have now is there's a gap between epsilon to negative 3 and epsilon to negative 2. So maybe you can do better. It might be important to get better results for the streaming, because there's dependency on epsilon, which I didn't tell you about. There's also other models, right? I told you that the cost model is 1 over ui. To get precision ui, the cost is 1 over ui. Maybe in other applications, a different cost model makes more sense, 1 over square root ui. So then, I don't know if this is the best bound. And more generally, maybe you can think of you want to estimate the summation of AIs. and you have some other non-standard, different way to access the AIs. We started in the first slide by you can only subsample. Some of them you see completely, some of them you don't see at all. In this precision sampling, you can see each one of them, but with some limited precision that you choose. Maybe there's another way to access the AIs that is reasonable for certain applications, and then it would give you a different sampling or estimation problem, and that sounds to me like a very interesting approach, how to sample summation via different like access mechanisms. That's it. Thank you.
Seems to be non-adaptive, namely you have to decide in advance what is the precision with which you sample each one of the AIs. But in the motivating example, you might do it in multiple stages. First you do some very coarse sampling and you get an idea that in certain territories you didn't encounter any member of that particular tribe, and then you don't spend extra effort there. So what happens if you allow the precision to vary as initial results of your sampling are coming in? Does it help?
So it's a good question. I think, I don't know the answer. I think it might be related to the fact that there's a gap between epsilon to minus 3 and epsilon to minus 2. So this gap, our algorithm is non-adaptive. It could come from either like getting better and better precision on some of the elements, or maybe you can do the AIs one by one in an order that you choose. Right? And then again, you adapt. You see some of the results and you choose the other one, which is almost the same question. And it might...
But also the precision. So I first...
so not asking something or asking later a bit higher precision, it's almost the same thing. Because you can... So if you didn't ask, it's like you got like a very good precision.
Okay, the full amount the second time around.
Well, it makes sense that you always at least double the precision, and then therefore it's geometric sequence, so it doesn't matter that much. You're right. So I'm saying it's almost the same question. And I think that it could be that the way to improve the epsilon to negative 3 is by being adaptive. That's something we thought about, or we don't know how to do it. Thank you.